In the following graphs, what edges would need to be added or removed in order for the graph to be a tree? Remember, the requirement for a tree is that you have a connected graph with no circuits. In graph A, we can see that we currently have a circuit. We can go from A to D to B to C and back to A. So we're going to have to eliminate one of those edges in order to break the circuit. I've replicated the graph here, and there are actually a number of solutions to this problem. If I take out this edge, we now can see that there is a tree, everything is connected, but there is no circuit. Remember, there's no connection point here in the center, so that gives us a solution. However, I could have also taken out one of the cross pieces, and I also still have a tree with no circuits, so it is also a solution. In question B, there are also several solutions. In this case, we're adding edges to the graph. Adding A to B gives us a connected graph with no circuit. We could, of course, done something like E to C as well, or E to D. In question C, we've again got an unconnected graph, so we need to make it a connected graph without making a circuit. There are again several possible solutions. I can connect A to C, or C to B, or D to B. Lots of choices. They all give me a connected graph without a circuit. Finally, in question D, we've got a connected graph, but we can see that we've got a circuit going on here between A, B, and E. We need to get rid of one of those edges to break the circuit. Now, there's no longer a circuit going on, so we have a tree. The sewage lines in a city need an upgrade, and every neighborhood must be connected, either directly or indirectly, by a sewage line to the purification plant. The graph below represents the neighborhoods in a city and the cost of upgrading the sewer lines in thousands of dollars. What is the minimum cost for the city to upgrade the sewage lines? To solve this problem, we're looking to minimize cost for the city to upgrade the sewage lines. As a result, we're going to start by looking for the edge with the smallest weight and begin with the process with that. Looking at the graph, D to B has the smallest weight, so I'll make that connection. Next smallest weight is B to E with a weight of 11. After that, it's B to C with a weight of 12. Now C to E has the next smallest weight, but that creates a circuit for us, so it won't be included. I also see that D to E has a weight of 12, but that creates a circuit, so it will not be included in the graph. I move on to weight 13, but the same thing occurs there. C to E creates a circuit for us, so it also won't be included. After that, A to D is the next smallest weight with a weight of 14. Then D to P has a weight of 15. At this point, we've connected every vertex in the graph, starting from the smallest weights and building up. We're asked to find the minimum cost, so the minimum cost now is just the process of adding up each of the weights in the graph. 15 plus 14 is 29, plus 10 is 39, plus 11 is 50, plus 12 is 62. And they told us it was in thousands of dollars, so we add 3 zeros at the end for $62,000. The cost of hiring a taxi is based on the amount of time it takes to get from starting point to your destination. The graph below represents a taxi ride's travel time in minutes between intersections. If a taxi costs $1.50 per minute, calculate the minimum cost to get from point F to point B, and then calculate the minimum cost to get from point A to point D. Let's start with the minimum cost from point F to point B. We begin by duplicating the vertices from the original graph. Now, because we're being asked to look for the minimum cost, we're going to start with the edges with the smallest weights. In this case, the smallest weight is the edge F to D, which has a weight of 3. After the weight of 3, the next smallest is from E to F and A to B. They're both 5. After 5 comes 6, which is edge C to D. The next smallest is 7, joining A to E. The next smallest is from B to C, but if we connected that, that creates a circuit, so we're not going to use that edge. The next smallest would be edge E to B, which has a weight of 9, but by including that edge, we would be creating a circuit. Since we can't create a circuit, we can't have that edge, After that, we look to the next smallest edge, which would be G to F. We now have a tree of optimal value. Using our tree of optimal value, we can see that to go from point F to point B has a weight of 5, 10, 17. If we multiply that times 1.5, we get $25.50, or $25.50. The minimum cost to get from point A to point D is 15. 7 plus 5 is 12, plus 3 is 15. Multiplying that times 1.5 gives us $22.50. Recapping the main points in this lesson. A tree is a connected graph with no simple circuits. A tree of optimal value selects only some edges in a graph so that all vertices are connected. There are no simple circuits, and then we use either the largest or the smallest weighted edges. There are several steps to creating the tree of optimal value. If we're looking for a minimum value, we copy the vertices of the graph, select the edge with the lowest value, and add it to our new graph. Then, of the remaining edges, we select the one with the lowest value and add it. We keep selecting the smallest edge and adding it to our graph, unless an edge creates a simple circuit. If it creates a simple circuit, we skip that edge and move on to the next one. Once you've created a tree, you stop adding edges. Creating a tree of maximum value is basically the same process. Instead of selecting the edges with the smallest value, you select the edges with the largest value.